NASA scientists are one step closer to unlocking the secrets of the universe. The James Webb Space Telescope completed its final deployment sequence just yesterday. For the first time in the history of astronomy, humanity has laid eyes on a truly unprecedented image, one that has stirred awe across the scientific community and ignited the imagination of the public. The James Webb Space Telescope, the crown jewel of modern space exploration, has just delivered the clearest and most detailed image ever captured of Proxima B, an exoplanet orbiting the closest star to our Sun, Proxima Centauri. This breakthrough isn't just a feat of engineering and optics, it marks a transformative moment in the search for life beyond Earth and deepens our understanding of the cosmos in ways previously deemed unattainable. Before we start, hit the like and subscribe buttons for more exclusive news. When the image was released, it revealed Proxima B not as a mere blip on a data graph or a hazy point of infrared light, but as a world tangible, textured, defined Webb's advanced near-infrared camera, near-cam, and mid-infrared instrument or MIRI combined forces to pierce through the cosmic dust and electromagnetic interference that have long shrouded exoplanet observations. What emerged was a crisp, high-resolution image showing Proxima B with astonishing clarity, surface albedo differences, atmospheric layers, and even polar ice caps could be inferred from the spectroscopic and visual data. While it is still far from the kind of planetary portraits we have of Earth or Mars, this image brings us dramatically closer to seeing alien worlds not as ideas but as places. The significance of this image lies in what it represents: a moment of astronomical maturity where theory collides with direct observation. For decades, exoplanets like Proxima B were primarily known through indirect means. They were detected by the telltale wobble of their host stars or by the minute dimming that occurred when they transited in front of them. While these methods allowed scientists to infer the presence, mass, and orbital dynamics of exoplanets, they left enormous gaps in understanding their composition, climate, or surface conditions. The James Webb Telescope, with its revolutionary ability to isolate planetary light from the blinding glow of nearby stars, has shifted the paradigm. It's not just about finding planets anymore, it's about characterizing them. Proxima B orbits within the habitable zone of Proxima Centauri, a red dwarf star located a mere 4.24 light-years away. This zone is the not too hot, not too cold region where liquid water could theoretically exist. On a planet's surface, the planet itself is roughly 1.3 times the mass of Earth, placing it firmly within the terrestrial category. Unlike the gas giants and ice worlds that dominate many exoplanet discoveries, these attributes alone have long made Proxima B a tantalizing subject, but the challenge has always been visibility. Its proximity to its dim, yet highly active star meant that previous instruments couldn't isolate enough detail to say anything definitive about its atmospheric or surface characteristics. The Webb image changes that the telescope's advanced coronagraphs and photometric filters enabled scientists to suppress the starlight of Proxima Centauri with unprecedented precision, allowing them to focus solely on the faint reflected light of the planet. What they found were atmospheric absorption lines that suggest the presence of key compounds, carbon dioxide, possibly water vapor, and tantalizing hints of methane. While none of this confirms the presence of life, the chemical signatures are consistent with environments that, at the very least, are not hostile to life as we understand it. There were also temperature readings derived from the thermal emission data, indicating moderate surface temperatures that fall within the bounds of Earth-like conditions beyond the immediate Implications for astrobiology. This image of Proxima B offers a snapshot of what Earth-like exoplanets might actually look like. The terrain appears variegated with regions of higher reflectivity, potentially indicating ice or desert-like expanses. There are darker zones that may correspond to oceans or heavily clouded areas. Even the planet's faint reddish hue, likely influenced by the light of its red dwarf star, gives a sense of alien familiarity, different yet strangely comprehensible for planetary scientists and artists alike. This visual context provides a new baseline for imagining what other rocky exoplanets may resemble. The excitement this image has generated stems not only from what it shows but from what it proves is now possible. Capturing an image of an exoplanet at such clarity is a milestone in observational astronomy. It demonstrates that with the right instruments and techniques, even planets orbiting distant stars can be resolved and studied with unprecedented detail. This opens up a wide field of research opportunities, from climate modeling of exoplanets to the study of planetary evolution in other star systems. It also means that the search for extraterrestrial life has become significantly more tangible rather than speculating based on indirect indicators. Scientists can now begin to analyze actual planetary conditions. It is also a moment of profound philosophical impact. For centuries, the question of whether we are alone in the universe has haunted our species. While we have found microbial life to be remarkably tenacious on Earth, thriving in acidic lakes, frozen tundras, and boiling vents, translating that resilience to other worlds has remained speculative. With this image, the bridge between speculation and observation narrows. If planets like Proxima B are this Earth-like in appearance and composition, it suggests that the ingredients for life may not be as rare or unique as once feared. Moreover, the fact that such detail was obtained from a planet orbiting a red dwarf star is a powerful testament to Webb's capabilities. Red dwarfs are the most common type of star in our galaxy, making up approximately 70% of all stars. If planets orbiting these stars can be imaged with this level of detail, it exponentially increases the number of potentially observable habitable worlds. Webb's success with Proxima B sets a template for studying other promising candidates, such as those in the TRAPPIST-1 system or LHS 1140b, further expanding our cosmic horizons. One of the most fascinating aspects of this achievement is the interdisciplinary collaboration it represents. Astrophysicists, engineers, chemists, planetary scientists, and computer scientists all played a role in designing the imaging algorithms, calibrating the instruments, and interpreting the data. The Webb image is as much a triumph of data science as it is of optics. Advanced machine learning algorithms were used to reconstruct the faint planetary light from noisy data, ensuring the final image was both accurate and rich in information. This integration of human ingenuity across fields demonstrates that space exploration is no longer the domain of isolated disciplines. It is a symphony of knowledge working in concert. The release of the image also reinvigorates public interest in space science. Visual evidence carries emotional weight. Seeing a distant world with our own eyes, albeit through the lens of an orbiting telescope, makes the universe feel a bit more reachable. The image of Proxima B, with its Earth-like silhouette and mysterious surface features, doesn't just reside in scientific journals. It's now part of our collective imagination. Schools, planetariums, museums, and online platforms are already using it to inspire the next generation of scientists, engineers, and dreamers. From a technical perspective, the precision of this observation reflects decades of progress. Webb's mirror alignment, thermal stability and adaptive optics all had to function flawlessly to deliver this result. The telescope had to compensate for not only the vast distance to Proxima Centauri but also for the rapid orbital motion of Proxima B around its star. This required predictive tracking algorithms and real-time calibration to avoid image blur. The data acquisition took several weeks with multiple orbits observed to confirm consistency and minimize the effects of stellar flare activity, a common issue with red dwarf stars. These achievements, while astounding, are only the beginning. Scientists are now using the data to build three-dimensional models of Proxima B's climate and surface structure. These models will help estimate the planet's rotational dynamics, atmospheric circulation patterns, and potential for magnetic field generation, all critical factors in assessing long-term habitability. If the planet does possess a magnetic field, it would offer protection from the frequent stellar flares emitted by Proxima Centauri, further enhancing its chances of sustaining life. The implications for future missions are profound. With the success of Webb's imaging of Proxima B, discussions have intensified around launching dedicated interstellar probes. Projects like Breakthrough Starshot, which aims to send Graham-scale spacecraft to nearby star systems using laser propulsion, now have clearer targets and more precise mission parameters. Knowing what Proxima B looks like, what it's made of, and how its atmosphere behaves will guide the design of instruments and trajectories for these missions. The vision of sending robotic explorers to neighboring star systems is no longer science fiction. It's a strategic goal grounded in real data. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us what are your thoughts on the James Webb image of Proxima B? Any big implications? We want to hear from you. Thank you for watching and see you next time.